to this advanced conduction lecture series. So this is the lecture 11, and in the previous lecture we formulated the one-dimensional unsteady or transient heat transfer, conduction heat transfer through a slab, right? And I formulated the problem both in dimensional terms and the non-dimensional terms, and I told that you should choose judiciously the non-dimensional terms if, only if, the non-dimensional terms are not mentioned in the question paper. Otherwise you have to use those only, you cannot choose by yourself. But if it is asked that you have to choose the non-dimensional terms by yourself, then you choose them in a proper way so that your algebra and your mathematical description of the problem gets simplified. So today is lecture 11, and today I will talk about the solution of the above governing equation and the boundary conditions. Okay, so it is lecture 11. Now the name of the method of the solution, okay, is called the method of separation of variables. Okay, now during our B.Tech or BE, we must have studied the engineering maths, and in engineering maths it is a very much well known method to solve the differential equations, right? So but unfortunately in most of the Indian colleges, including some IITs also, students don't have that much knowledge about engineering mathematics. When I studied in my BE in Jadavpur University, so some of the course, we have a segregated engineering mathematics course, that is, in first semester we have some of the parts, in second semester we have some of the parts. So some of the parts were taught very well, really very well, and I also studied some of the parts by myself during the gate preparation. Okay, and even uh, today itself also I do study some good, some concepts which are essential for any field, okay, of engineering. I study those parts of mathematics uh, even today also. Okay, so what I suggest you is, see, uh, you cannot proceed through any engineering course or through any engineer without the knowledge of engineering mathematics. You don't have to study the whole deep level mathematics, but you must have the knowledge of engineering mathematics. Okay, so enough talking about that thing. Now let us proceed. So the name of the method is a method of separation of variables. Okay, so as the name suggests, we have to separate the variables. See, in this governing equation the unknown variable is theta, right? So here theta is a function of what? X bar and tau, right? X bar and tau. So what is the first step that comes from the name itself, and that is we have to separate this variable and we have to write, so let theta is and which is a function x comma tau, I will write this as what? Some a which is a sole function of x bar into some b which is a sole function of tau. Okay, now uh, you might be thinking that why this kind of breaking, that some a into b, I could have break I could have broken this function like a plus b, or maybe a into b is okay. So all these combinations are possible in this method. You could have broken like a into b with some coefficient a plus another coefficient b with only b plus another coefficient c with only a. All these combinations are possible. So again, method of separation variable is a very deep part of mathematical of engineering mathematics. So if you want to dive deep into that, how this came and how the how this came and all the things, that is what is the basic motivation or what is the basic nature of thought which concluded this thing. Okay, so for that uh, you must concern any uh, good engineering mathematics book, okay, like BS Grewal and all. But for the time being we are happy enough if we are able to solve this one dimensional transient conduction equation. And for most of the problems in mechanical engineering which requires the method of separation of variable, uh, for them this kind of separation is more than enough. Okay, so let us proceed with this. So this is the first step. Okay, then what I will be doing is, so substitute this theta, I will write substitute uh, this theta equal to a into b in the governing equation, right? So what is the governing equation? Let me write it again. The governing equation is your del 2 theta del x bar 2 is equal to del theta del tau, right? So we have to put here a into b and also here a into b. Okay, now if I put here a into b, then see this b is not a function of x bar, so I can take out this b outside and I can write d2a dx2, right? Similarly, if I put here a into b, you notice that this a is not a function of tau, so I can put this a outside the derivative and I can write a into db d tau. Clear? So that is what I will be writing in the next step, and that is b into d2a dx2, that is equal to a into db d tau. And in the next step I will be just interchanging this a and b. Okay, and I will be writing this. Okay, so now you see that here this a is a function of x bar only. Similarly, this is also a function of x bar only. Similarly, this is a function of tau only, and this total thing is a function of tau only. Clear? That means we have a function of, this is a function of x bar only, okay, and this is a function of tau, right, only. Now you see that if I have a function of, let us say this is g of x bar and this is h of tau, okay. Now I have g of x bar equal to h of tau for any x bar comma tau pair, okay. Like I have one function that is x square, another function that is x. So both of them are equal at x equal to 1. Okay. So therefore, if the equality holds at a particular pair, then I cannot say that these are equal. Okay. And also the equality holds if x equal to root 2. Okay, and no, only x equal to 1. Okay, so I cannot say that x square equal to x for all x. Okay, but if it holds that it is a sole function of x bar and it is a sole function of tau, then if it has to hold for all points in x bar comma tau pair, then it must be a constant. Both the functions must be a constant. That will be the only case where f of x equal to g of y for any pair of xy. Okay, so now following the same logic, that means this is equal to a constant and that I write as mu s. So this is termed as the separation constant. Okay, So this was a very important statement. That is why these two things are boiling down to a constant. Okay, so this is mu s. Now that means from here we are getting two equations. Okay, from this whole thing we are getting two equations. And what are those two equations? The first is this one, and the second is this one. Sorry, it is equal to mu s, and the second is this one. Okay, so first let me talk about the sign of mu s. Okay, sign of mu s, and what should be that? So here we will be working with this equation. Okay, this I say as equation small a, and this I say as equation small b. Okay, so here I will be talking about the case 1. Let us say that mu s is greater than 0. Okay, and keeping this in mind, we will be solving the equation small a, right? So I will be quickly solving this. Okay, and this will be your we will be seeing that s is okay. I will be solving this without any step jump. Ln tau is equal to mu s into tau plus some constant c1. That means b is equal to some c2 into e to the power mu s into tau, where this c2 is equal to e to the power c1, right? Okay, so now you see that if my tau is greater than 0, that means with if my tau is increasing, then my b should also increase. And what is tau? Tau is the time by some t reference. So tau increasing means what? Tau increasing means my time is increasing. So with the increasing time, this b must also increase if my tau is greater than 0. Sorry, not tau, what I am writing. If my mu s is greater than 0. That is, I am talking about this fact that if this number is positive, then if I increase this tau, so let us say that I have some a to the power 4 tau. Okay, so you can see that e to the power 4 into 1 is less than e to the power 4 into 2. But if I had e to the power minus 4, then e to the power minus 4 into 1 is greater than e to the power minus 4 into 2, right? That means if my mu s is positive, then if I increase the tau, that is with the increment in time, my b should also increase. That means b is not having any upper bound, and if b is not having any upper bound, then my theta will not also have any upper bound. That means as my time uh, as my time goes on, as my time proceeds, I will be seeing that my temperature of the slab is going up, and without any steady state. Okay, without reaching to any steady state, and that is truly unphysical. That is not possible. Okay, so this is, so that means, and this whole argument means that theta is not having any upper bound. Clear? Okay, so this is unphysical. This is unphysical, and that means mu s is surely less than equal to 0. Mu s is not greater than 0. Okay, now let us case the second case, that is mu s is equal to 0. Okay, so if mu s is equal to 0, then this equation boils down to b is equal to c2 into 1, because this is e to the power 0 and that is 1, that is c2. That means b is equal to a constant. Okay, if b is equal to a constant, then my theta becomes some constant into a, and a is only a function of x bar. That means my theta is only a function of x bar. That means my theta is not varying with time, and that is a trivial solution of this problem. Okay, that is, I can have two, I can have uh, one temperature at this wall and one temperature at this wall, and I always can have a steady state solution. But I want to find the unsteady state solution, that is the transient solution. For that, if I am having that my b, which is only a function of tau, and because of which the theta is a function of tau, if my b is boiling down to a constant, then I cannot have theta as a function of time. Then my time dependence is gone, and I don't want that. So this leads to a conclusion that my time dependence of solution is gone, right? And I don't want that. Not I. Here it is we, right? We don't want that. We don't want that. So now clearly that means mu is less than 0. This is our conclusion. This is a very important conclusion. I am highlighting by 3 separate colors. This is a very important conclusion. So in method of separation of variables, you can integrate that governing equation, okay, and you can show that mu s must be less than 0. But here I am not going into that much mathematical details. You can always consult some good mathematical book, good engineering mathematics book. And also I don't think that good engineering mathematics books also have that much description that why mu s is negative from the mathematical point of view. That is why here I am showing you the physical approach to verify that if mu s is less than 0 or greater than 0 or equal to 0. See, one approach is, that is, you put the value there and you see that what happens. Another approach is you go through a approach of a pure mathematician. So we are engineers, so I think this approach is more relevant to an engineer. Okay, so here we got this one, that mu s is less than 0. So here we let that mu s is a constant, that is minus lambda square, where this lambda is not equal to 0 and lambda obviously belongs to the real line. Okay, so if mu is equal to minus lambda square, then following this equation, so this equation maybe I will term as equation small c. Okay, so from equation small c, my b is equal to c2 into e to the power minus lambda square into tau. Clear? I will term this as my equation small d. Okay, now let us take the second equation. Okay, let us take the second equation. And what was the second equation? That is small b. Okay, so if I write the second equation, that is 1 by a d2a dx2 square is equal to minus lambda square. So this was equal to mu s, and mu s is equal to minus lambda square. So we get this equation, right? Now that means this is, I can just do some algebraic manipulation and this boils down to this, and this I can write out d square plus lambda square is of a is equal to 0. So this is an operator where my d is equal to d dx. Okay, d dx bar. Okay, so if you have studied your differential equation part in your engineering mathematics, then you already know that this has the auxiliary this. So this is my auxiliary equation for this differential equation, and this means d is having the root plus minus lambda. Is it plus minus lambda or plus minus I lambda, right? Lambda into I is the imaginary number where this I is equal to root over of minus 1. Okay. So here we can write this as, okay, I will do the whole mathematical steps so that you remember. I mean, so that you, sorry, not remember, so that even you forget the ultimate result, but you should be able to derive that from scratch. So here there are two roots, d1 and d2, right? So d1 is equal to lambda I, d2 is equal to minus lambda I, right? So therefore we can write the complementary function CF is equal to some constant, maybe k1, okay, into e to the power d1 and what is the independent variable, x bar, plus k2 into e to the power d2 into x bar. So here my d1 is lambda I, so I have my I lambda x bar as exponent plus k2 into e to the power minus I lambda x bar into exponent, I mean as exponent, right? Now e to the power I theta is equal to cos theta plus I sin theta. So then I can write this as cos lambda x bar plus I sin lambda x bar, right, plus k2 cos of minus lambda x bar, but cos of minus lambda x bar is equal to cos x bar, cos of lambda x bar, but sine of minus lambda x bar is equal to minus sine of lambda x bar, right? So now if I take this cos term common, then I can get k1 plus k2, right? And if I take this sine term common, then I can get my I sine term common, obviously, or I can take this I into the brackets. So I get I k1 minus I k2, okay. So now I will term this as some maybe C2, or C2 I have already used, so I will term this as C3, and this I will call C4. So I am getting this is equal to some C3 cos of lambda x bar plus C4 sin lambda x bar, okay. So you saw what happened, that if I have this kind of a equation, then we get the solution as A is equal to C4 sin or cos. So let me be consistent with the things, okay, C3 with cos here, right, C3 with cos, okay. So C3 with cos lambda x bar plus C4 sin lambda x bar, right. So I was having lambda square here, I have that lambda here, into I was having x bar here as my independent variable, so here also I am having x bar. So had I had here lambda, then this would become root over lambda, right, okay. So the same differential equation you got in your SHM, okay. So when we are taught the SHM in class 12, right, or class 11 maybe, I don't recall exactly. So then we are directly being told that this is the equation for SHM, that is A equal to, that is Y equal to some A into cos omega t, right, like that, okay. But this and if you have studied your engineering dynamics course, okay, that is not engineering dynamics, that is dynamics of machines or theory of machines. There you must have studied the vibration part, and in the engineering level, in the mechanical engineering part, you must have studied this governing differential equation, right? And there you must have saw this. Okay, okay, so now I have got this equation. So here what are the unknown constants? So first of all, we don't know this lambda, we don't know this C2, we don't know this C3, and we don't know this C4. Okay, so here we have unknowns are, now unknowns are, okay, lambda, C2, C3, C4, but we have only three boundary conditions, that is two boundary conditions and one initial condition, right? So let us say that how can we find all these things? Okay, so now we have to put our boundary conditions one by one. So let us look at our boundary conditions, and what I will do is I will copy these boundary conditions from here. Array, I forgot to copy. Okay, paste. Okay, it is okay now. So what there was written, that is these two are homogeneous. No, this is only my homogeneous equation, right? Homogeneous, this part is homogeneous, right? Okay, so now you see I will talk about a rule, that is to apply the method of separation of variable, you must have only one inhomogeneous equation. So in this description of the problem, we have all total how many equations? Two boundary condition, one initial condition, and one governing equation. So out of this four equation, we need only one inhomogeneous equation, and all other equations must be homogeneous. Only then we can apply the method of separation of variable. So you put this fact into your mind. So this so see that this is a method. Okay, mathematicians have developed this method, and there are some conditions for which this method will apply. So you have studied various methods during your JEE and all other exams for finding integrals, right? For doing integration, that if this is the form, then apply this, if this is the form, then apply this. Similarly, this is also just a method to solve an equation. Okay, and this kind of equations where we have this kind of governing equation that is homogeneous, and two homogeneous boundary condition and one inhomogeneous um, initial condition, we term this as, not all the equation of this kind, but some of the specific equation of this kind, we term these as Sturm-Liouville solution equations. Sturm-Liouville equations, STRUM, and I don't recall the spelling of Liouville exactly, that is maybe LOUVILLE, maybe. Okay, so you can go through the mathematics books, and also you can search directly into Google the Sturm-Liouville equations, and those are very famous equations. Okay, so you can clearly see here that here we have our governing equation, homogeneous, right? Homogeneous, and we have our governing equation homogeneous, one boundary condition homogeneous, but we have two equations inhomogeneous here. So I talked about the homogeneity and inhomogeneity, that is other than theta, that is the only dependent variable, we have another constant here, that is 1. And in this equation also, other than theta, we have another constant here, that is this one, Ti minus T1 by T2 minus T1. So for an equation, be it an algebraic equation, be it a differential equation, for an equation to be a homogeneous equation, you must have only the independent variable. Obviously you can have the derivatives or the integral of that independent variables, okay, but you cannot have any other parameter than that, okay. You can have only the independent and dependent variables, okay. So then what, so then I mean, if we cannot apply the method of separation of variable here, then all our, I mean, all these hectic descriptions of mu s and this solution of this differential equation, so do all this go in vain? No, because ultimately what we will do is, when we don't have only one, I mean, in other words, when we have more than one inhomogeneous equation, we break that problem into number of problems where that number is the number, I mean, that number is the number of inhomogeneous equations. So let me repeat that. I think I was not able to convey that very clearly. That is, here we have two inhomogeneous equation, that is we have two inhomogeneous equations, right? So we will break the problem, into two parts, okay. So let us see how can we break that. So before that, I will talk about another concept of engineering mathematics. So have you heard about the linear differential equations? Linear differential equations. So linear means we have only the addition or subtraction of the dependent variables or their derivatives or integrals clear, okay. So that means if you are having maybe d2 theta dx bar 2 minus d4 theta by dx bar 4 plus theta, okay, then you can have plus d3 theta dx bar 4, anything like that, plus some theta into a plus, okay. So all these have in their own coefficients, a b c, small d is equal to 0, and all these coefficients, okay, all these coefficients are constants, then this is a linear differential equation. And if you have this kind of equations, then see, if I have theta 1 as a solution and theta 2 as a solution, right, then if you put theta 1 plus theta 2 here, so see what, if theta 1 is a solution, then if I put here theta 1 everywhere, then this will this will satisfy this equation. If I put theta 2 here, then theta 2 will also satisfy this equation, right? But if I put theta 1 plus theta 2, then that will also satisfy this equation, right? But had I had this kind of equations, that is theta into d2 theta dx2, then you cannot say that theta 1 plus theta 2 is a solution of this equation. If this is equal to 0, and if here theta 1 is a solution, right, and theta 2 is a solution, then if you put theta 1 plus theta 2, okay, and this one also, then this is not a solution. This you cannot get. This you can verify by yourself. That is, you put theta 1 here. I am just showing these things to you guys so that you do not forget it, and you don't feel like you have to mug up all these things. That is when we can separate or when we can break the problem into various problems, only if the problem is a linear problem. So then you just add these two equations. So if you add these two equations, then this is not equivalent to having this. Is not equivalent to having this. Am I right? So if you could get this thing by adding these two, then you could have said that my theta 1 plus theta 2 is a solution. Like here, as all these terms are linear, you put theta 1 everywhere here, and then you put theta 2 everywhere here, then you add those two equations, then what you will have? I will just work out with the first term. We will have a is a constant, I can take it common, and d d2 theta 1 dx2 plus d2 theta 2 dx2 dx bar 2. So this you can write as this, right? Similarly, in every term you can have theta 1 plus theta 2 instead of theta. Then you can say that my theta 1 plus theta 2 is also a solution. Okay, clear? So here also our governing equation, that is this one, this is a linear differential equation. If you put theta 1 and theta 2 and add them, then you will get, instead of theta 1 plus theta 2 here. That means if theta 1 is a solution and theta 2 is also a solution, then I can say that theta 1 plus theta 2 is also a solution. Okay. So I am not removing these things. That is, if I have to send you the notes by any means, maybe I can create a group if you guys want. Okay. So then these things will be of very significance. So now let me proceed. So I will break the problem. So next step is, let us break the problem. Okay. And essentially this step is called as principle, sorry, what I am writing, not principle, it is principle of superposition. Okay. That is, you can superpose two separate problems to get a different problem. Okay, that is, I can take out your hand, I can take out your this hand, then I can call your this hand, your this body part and your this hand are separate body parts, and then you can join them to have your body. Okay, so your hand is a separate thing, your this hand is a separate thing, and your this body is a separate thing, but when you join all those things, then you get a full body that is altogether a separate thing, right? So that is the principle of superposition. You have the problem 1, you have the problem 2, maybe problem 3 and 4, then you can join all those 4 problems to get a totally different one. Okay, so here let us see how can we break the problem. So actually we are doing the vice versa thing, that is, instead of joining the problems, what we are doing is we are breaking a complicated problem into 2 simple problems, and we solve them, separately to get a different uh, problem. Okay, so I will actually stop this lecture here because I have a very important work to do, and so I will surely complete the whole solution in the next lecture. Okay, until that I will suggest you go through some mathematical books and the internet sources, and you look through the principle of superposition and the method of separation of variable. Okay, if you want, if someone wants to dive, if someone wants to go too deep into that why mu s is negative, I want to know the mathematical background, okay, that how it can be proved through integration of the governing equation and all, then you can go through some good resources. Okay, if it is possible, then I will put some resources in this video. So